Okay, in this section, I'm going to be discussing in detail what degeneracy is for the simplex algorithm and how we're going to overcome the degeneracy. So, from the previous section, we define what the simplex tableau is, right? So, a simplex tableau is completely defined by its BFI. The BFI determines the basis matrix, and knowing the basis matrix, we're going to be able to compute A bar, B bar, C bar, and theta bar. And associated with the simplex tableau, we've seen that we have a basic feasible solution where we set the non-basic variable equal to 0. This is B complement. And then the basic variable, we're going to send them to the right-hand side. And for this basic feasible solution, the value of our objective, C transpose X bar, that's equal to this number here. So what is degeneracy? Degeneracy is simple, that in addition to the non-basic variable equal to 0, we have some basic variables equal to 0. That's degeneracy. So let's define what let's put the definition here. A BFS is degenerate if one or more basic component is 0. Very simple definition. Okay. So in addition to the non-basic being 0, we have one or more basic component 0. Then we say that this BFS X bar is degenerate, and then we say that the linear program itself is degenerate. Now, so remember how the BFS is calculated. BFS is we set the basic variable equal to the right-hand side. So degeneracy is when you see a 0 on the right-hand side. If you see a 0 on the right hand in any simplex tableau, then you say this linear program is degenerate. Okay. So that's a very simple definition. Now, why is degeneracy an issue? Let's go through that. So let's say that this simplex tableau is degenerate. I have a 0 somewhere in here. And let's go to a simplex pivot. So I'm going to choose a pivot column, right? And I'm going to choose a pivot row. Okay? So I'm going to pivot on this element. Okay? I'm going to be doing a simplex iteration. And we're assuming that this is there. So there's a 0 somewhere here. And it so happened that that 0 happened to be on the pivot row. I have a 0 here. Okay? So what happened after I do a pivot? After you do the pivot, this number is not going to change. Because what are you going to do? You're going to do this row minus a multiple of this row. But since there is a 0 here, this theta bar doesn't change. So therefore, we're going to move to another simplex tableau, another BFS, where the objective function stays the same. And that's where the issue is. So let's say, for example, we are at the simplex tableau TU, okay? And then we do a simplex iteration. We go to another tableau TU plus 1, and so forth, till we go to tableau TV, okay? And let's say the pivot row, right-hand side of pivot row, is 0 in all this iteration. Then what you're going to have? You're going to have theta bar, and I'm going to index it by u. That's equal to theta bar of u plus 1, etc., equal to theta bar of v. Okay. In other words, in all this iteration, I wasn't able to reduce the objective function. Then it's possible that T sub v is equal to Tu. Because we weren't able to reduce the objective function, then when I arrived here, it so happened that this simplex tableau is exactly this simplex tableau. In other words, they share the same BFI and everything else is the same. And that's where so this becomes like a cycle. And this cycle, the simplex algorithm will not be able to get out of this cycle because it's going to do the same operation from here to here and so forth. And in the literature, there is an example of this happening. So degeneracy is an issue. So we have to deal with that issue. Now, the first method to overcome degeneracy is called the Bland rule. So let's go over the Bland rule. So it gives us, the Bland rule would give us a way to choose the pivot column and the pivot row. So the pivot column how to select the pivot column is we do the minimum of I, C bar I negative. Okay, that's the pivot column. In other words, we go in here, we start from here, and we go down, and the first time we hit a negative number, that's our pivot column. Okay, whereas the simplex, the regular simplex, it looks at all the element and chooses the most negative C bar. That means that it's taking the steepest descent. In other words, it's looking for an iteration making the biggest decrease in the objective function. Here it's not. It just looks for the first I such that C bar of I is negative. So that's how we choose the, let's call this R. Okay. 2. Now we have to choose, now that we selected the pivot column, we need to choose the pivot row. Well, the pivot row, obviously, we have to maintain the right-hand side being non-negative. So we have to do the minimum of B bar of I over A bar of I R for all the A bar of I are positive. So the regular ratios, all right? We have to do the ratio. This maintains, when we do the iteration, it will maintain the right-hand side being non-negative, okay? So when we do this minimum, so we're doing the minimum on every row. So when we do this minimum, if the minimum is unique, that's our pivot row. But suppose that it's not unique. There is a tie, okay? In case of ties, so let me write it here. Then we have to choose, I'm going to call it P, the pivot row. It's equal to the minimum of beta I, where beta I is equal to the argmin of this expression here. Okay, let me give an example. Suppose that I have, here's my ratios, B bar of I over A bar of IR. Let me pick some examples. So let's see, 4, 2, 5, 2, and 6. Okay, and let's put the BFI right here. Let's say this is 7, this is 4, 1, 3, and 8. Okay, this is my ratios, and this is my BFI. So now I do this minimum, all right? So my minimum is here and here. Okay. So I have a tie in this case, and therefore my linear program is degenerate. Then Bland rule says to look over the BFI. and select the minimum of these. So the minimum of these will be this one. And this is my pivot row. Okay, that's what blend rule is. Often people will say pick the top row. It's not the top row. It's really you have to look to the BFI and you have to take the minimum indexes for those rows where the tie is, and that's where your pivot row is. So this is what blend rule is. So let's go through the proof for blend rule. Now fact. Let me write down fact. The simplex under blend rule does not cycle. Okay? We never have a situation like I explained before, where we do many iterations and then we end up with the same simplex tableau. Under blend rule, the simplex does not do that, and therefore, because it doesn't cycle, then the simplex is finite. It will terminate in a finite number of iterations, and the reason is because there are only a finite number of simplex tableau. This beta is a subset of a finite set. There are only a finite number of these BFIs. So that's why the simplex will terminate in a finite number of iterations. Okay, so let's assume that the simplex under blend rule cycles. So there is a cycle. We're going to assume so I have a tableau TU, then I move to another tableau TU plus 1, etc., to tableau TV, and this is equal to TU. All right? So these two tableaus are equal. So therefore, we're going to assume this, and then we're going to arrive at the contradiction at the end. So the theta bar of U and the theta bar of V, these two are equal because TV is equal to TU, all right? And since the simplex, this theta bar in the simplex is a non-increasing sequence, so therefore this is equal to theta bar of U plus 1 equal to theta bar of V. So all the theta bar are equal in this cycle. And because we saw earlier when these two are equal, that means the right-hand side of pivot row is 0. 0 here, etc. It's 0 throughout the cycle. The right-hand side, if we look at all the pivot row, the right-hand side is 0. Now here we're going to classify the columns into 3 types in this cycle. One is I could have a column that's basic throughout. Okay, I have a specific column that's basic here into U plus 1 all the way to TV. Okay, that could happen. That's type 1. Type 2, I have a non-basic throughout. Okay, it's happened that I have a specific column that's non-basic into U, non-basic into U plus 1 all the way down. Okay, that's type 2. And then type 3, let's assume that I have a column that's basic into U. All right, so you got TU here, TU plus 1. So I have a column that's basic here, all right? And then it came out of the basis. It went out, all right? Okay, this specific column was basic here, and then it came off the basis right here. But because it's basic here, it's also basic here. Therefore, this column has to come back into the basis. Okay, so this is basic, and then basic, I label it like this way: basic coming out, and then non-basic coming in. Okay, so my variable was basic right here, and then it came out, and then after few iteration it has to come back in. All right, and the other case is I have a variable the other way around. I have a variable that's non-basic here, and at some point it came into the basis. Here it became part of the basis, but since it's a non-basic here, it's also non-basic here. So here it has to come out at some point before TV. It has to come back out. So here it's non-basic coming in, and then basic coming out. Okay, so that's the type variable of type 3. So they like this one here, it came in the basis and it has to come out, and it could happen a number of times, but it has to happen in pairs like this. If it comes in, it has to go out, and so forth. So these are the 3 types of when we classify all our columns in our thing. And from here, I'm going to define L to be the maximum I column I of type 3. Okay, so and this maximum is well defined, because we can't have only type 1 or type 2, right? We have to have some of type 3, because TU plus 1 is different than TU. So this L is the maximum index, maximum column, index of the column, such that column I is of type 3. So all the columns after L have to be either type 1 or type 2. Okay, so for this column L, so there is an iteration somewhere here. There is an iteration where it came in, and there is another iteration where it came out. Okay, and not necessarily in this order, because we have 2 cases here. So we have the other case like this, coming out and then coming in like this. Okay, so I'm going to call, let me erase this. So let me rewrite the definition of L right here. L is the maximum of I of type 3. Okay, so I have 2 tableaus, right? I have TP so I'm going to define it like this. A bar, I'm going to give it an index P, right? B bar, P. I have my C bar, then I got my objective function 0, -1, and minus theta bar of P, right? And in here, this tableau correspond to L coming in, basic coming out, right? So at some point here, so this is so here L, right? L is basic in here, so it's sorry. Let me write down the feasible index here. BFI. So L is, this is L, this row. L is basic, so it's in the BFI. So this row is coming out. All right. So and let's call and let S coming in. So here we have column S. Okay. So this is my entering variable S, and what's going out is this L, that's basic, this variable here, that's this column, that's basic. Okay. This is Tableau TP. And then Tableau TQ B bar of Q, B bar of Q, C bar of Q, and then our objective -1 minus theta bar of Q. Okay, so in here, remember this L basic coming out, so here L non-basic coming in. Okay, so Q is the iteration where L was non-basic, it was coming in. So this is column L. So this is the column we're gonna, this is the pivot column. L was non-basic coming in, but here it was non-basic, it was coming out. Okay, because L is of type 3. Now, let's write down the some equations here. So let me read this equation here. So Z, remember this is Z, right? That's equal to C transpose X. That's how it was defined. So that's equal to C bar of P X plus theta bar of P. Okay, just reading this equation. And the same Z over here, same Z over there, that's equal to C bar of QX plus theta bar of Q. Okay? But remember, during the cycle, theta bar is equal to theta Q, so that cancels out, and I get this equation, C bar of P X minus C bar of Q X equal to 0. And that's true for every X such that AX is equal to B. AX equal to B is our original system that these two are equivalent to. Okay, so now I'm going to expand this one. Okay, so it's equal to C bar of P beta minus C bar of Q beta times X plus beta, or the indices in beta, and then the complement of that, C bar of, let me write it different ways. I'll do the CQ. I mean, it's the same, I just prefer it this way. And then C bar of Q beta complement minus C bar of P beta complement of X equal to 0. Okay, I'm looking here, it's just the sum for all the indices in beta, and this is the sum of all the indices in beta, the complement of beta. That's just this equation expanded. Now this is equal to 0. Because this is the in C bar of P, the beta, the coefficient corresponding to the basic variable is 0. So that number is 0. And so what's left is just this. So let me write it over here. So I got C bar of Q beta times X beta. I'm sorry, this is beta and this is beta bar, beta complement. Okay. Times X beta plus C bar of Q beta complement minus C bar of P beta complement X beta complement, that's equal to 0. Okay, that's this equation. And that equation here, that's true for every x such that ax is equal to b. All right? Just reading from those two equations. Let's construct a solution to this system of equation as follows. So I'm going to define x star of s equal to some epsilon positive, okay, and then x star of I equal to 0 for I in the B complement and I not s. Okay, so in here I'm going to set this variable, this vector equal to 0 everywhere except for I equal to s. I'm going to set it to epsilon positive. So what's left is that in this system of equation, when I do that, then all the non-basic columns are multiplied by 0 except s, and what I'm left is the basic components. So I have a system of this form. I got the basic component here plus this is column s equal to b bar, right? So the basic component, this is the identity matrix here. So the basic component are equal to b bar minus this column times s. So x star of beta is just b bar of p minus a bar dot s of p times epsilon. Okay. So this is a solution of this system of equation. All right. Then it's also a solution to our system, our original system. So we could plug this into that equation on top, and I get the following. So here I only have one term, so it's the s term. So it's c bar q s minus c bar of ps times epsilon, right? Plus the sum of I equal 1 till m. I'm going to expand this one. So c bar of q beta I, right, times x of beta I, which is this b bar of pi minus a bar of pis times epsilon. All right, this is equal to 0. Okay, for this specific solution. So now, let's look at this term now. This term is positive by choice, right? We chose epsilon positive. Now this term here, this is the coefficient in Tableau TP, the coefficient for the S column. But remember, S is coming in, so this here has to be negative. We only pivot on column for which the C bar is negative. So that term is negative. Right. And now how about this term now? S was non-basic and it's coming in. So S cannot be of type 1 or 2. All right? Because it changed status. It was non-basic and it becomes basic. So therefore S is of type 3. Okay. And now, since L is the maximum I for type 3, then S must be less than L. So S is less than L. And since S is less than L, then this coefficient here, that's in TQ. So S is somewhere in here before L. Since L is coming in, blend rule says that this L has to be the first index that's negative. So therefore, this element C bar Q S is greater or equal to 0. It has to be. All right? And this is by blend rule. Okay? So this term is greater or equal to 0. This term is negative. This term is positive. So this whole term here is strictly positive. And therefore, this term here is negative. Okay? Now I'm going to look at every term of this, and I'm going to show that every term in this sum is greater or equal to 0, and that's where the contradiction occurs. Okay, so let's do case 1. I'm going to look at this beta I. So first, beta I bigger than L. Okay? I have a term for which beta I is bigger than L. Well, L is the maximum of I of type 3. So beta L not of type 3. Okay? Therefore, it has to be either type 1 or type 2. It has to be type 1 because it was basic here. Beta I is basic in here. Right? This is the beta. Okay? So the beta I was basic in here. So therefore, beta I of type 1. Now remember type 1. Type 1 is basic throughout the cycle. So beta throughout the cycle, therefore beta I basic in TQ. Right? And because it's basic in TQ, then the C bar of Q beta I, that's equal to 0. All right? Remember, we set the coefficient equal to 0 for the basic variable. So the term, this term here, for all beta I bigger than L are equal to 0. So the term here, I'm just going to put term equal to 0. And the term, I mean this product, this term here. So that's 0. That's case 1. Case 2, L is one of the beta I's. So here I'm going to put beta I star equal to L, right? So here beta I star, and that's L. Same thing as L. Okay. So my term here is just C bar Q of L times b bar of p I star minus a bar of p I star s times epsilon. So this is the term here. Right? Just replace beta I by L. Now, this term here L is coming in the basis, right? So therefore, the coefficient here, that's negative here, right? We only pivot on column for which C bar is negative. So this is negative. Now this term here, beta I star, that's the pivot row, right? So that's a pivot row. So I have a 0 right here. Remember, during the cycle, the right-hand side of the pivot row is 0. So that's equal to 0. Now this term here is this term here. So AR star S. So that's positive. We only pivot on positive elements. So this term here, that's positive. And epsilon is positive. So the term is positive for this case. So case 1 is 0 for this term. For this case, this term is positive. And finally, the last case, let me erase this now. Case 3, beta I less than L. All right? This beta I is less than L. Well, if it's less than L, so beta I is an index over here, okay? And L is coming in, all right? So that means this is the first time we saw a negative number. So therefore, C bar of Q beta I, that's greater or equal to 0. This is because of blind rule, right? So the coefficient is greater or equal to 0. Now, how about this parenthesis here? Well, we're going to have case 3. I'll call it 3A. Okay. Beta bar I positive. Okay. I'm going to assume in this case that beta R is positive. Now, if I choose epsilon very small, I could make this strictly positive times this is which is greater or equal to 0. So the term is greater or equal to 0 for epsilon small. Right? By making this term small, I could make this term greater or equal to 0. Now, case 3B, so the B bar is either greater or equal to 0 or 0. Remember, right-hand side is always greater or equal to 0. So in this case, I'm going to assume that B bar of P I equal to 0. Okay, and then I'm going to look to this term, two cases. A bar of P I S less or equal to 0, and then here I have case 3C, B bar of P I equal to 0, and A bar of I S P strictly positive. Okay, so these are the three cases. Now, for this case here, case 3B, so this is greater or equal to 0, this is 0, and this is less or equal to 0, and epsilon is greater than 0. So the term is greater or equal to 0. Right. Now, this case here, this is impossible. Because of blind rule. And let's look to this. So here we are in TP, right? So this is I star, okay? This is this is the pivot row. What does this say? That says that I have another row, I, right? For which I have a 0 here, right? And here I have positive term, a bar of PS, positive term, okay? Then we have two rows that are tied for the ratio. Remember when we did the ratio? 0 over this and 0 over this. So they tied. So blend rule would say that if you have if you have a tie between two rows, then you look over the BFI. So here, this is beta I here. So you look over to the BFI and you select the one with the minimum index. But in here, case 3, beta I is less than L, then I would have chosen this row instead of this row to pivot. So that's why this is impossible, because here we are assuming that this is L is basic and it's coming out. So this case cannot happen. Okay, and therefore, in any case, we showed that every term of this in this sum is greater or equal to 0, and actually case 2, we showed it that to be strictly positive. So therefore, here we showed that the sum of I equal 1 till m of C bar Q beta I times B bar of Pi minus A bar of Pis times epsilon. This sum here is bigger than 0. We just proved that for all those cases. And this is where the contradiction occurs. So we showed it before, it's negative, and here positive. So contradiction. So therefore, the simplex tableau under blend rule does not cycle, and therefore the simplex algorithm will terminate finite. So what I'm going to do is here, I'm going to pick a small epsilon positive. And then I'm going to replace B equal to B1, etc., Bm. Okay, I'm going to do the same thing. So the first equation represents a hyperplane, and it's equal to B1. I'm going to move that hyperplane by a small amount, epsilon. So let's call it B of epsilon. So I'm going to do B1 plus epsilon. So that's the first hyperplane. Now the second hyperplane, I'm not going to move it with the same epsilon. I'm going to move it with something different, like we did before. I'm going to move it by epsilon square, etc. To the last one, I'm going to move it by epsilon to the power m. So I kind of made some perturbation to the right-hand side, and this is the perturbation. Now, we're going to prove in a few minutes that the new program, the new LP, with this right-hand side, is non-degenerate. In other words, when we replace this B by this one, then whatever iteration we do, we're never going to see a 0 on the right-hand side. And therefore, the simplex does not terminate in a finite number of iterations. And once I do that, then now I solved my linear program with this right-hand side. Now I need to solve it now with b, without the epsilon. And remember, the b bar is just b inverse of b, right? The right-hand side without the epsilon, it's just b inverse of b. And the b inverse, we got it from the simplex using this right-hand side. So this is a way of getting over degeneracy. We're going to prove that this is true. There are two issues with this method right here. Number one, I said pick small epsilon positive. I didn't say how small. So the issue is how small. Right? We're going to prove in a minute that this is the line plus infinity and 0. There is a number r that if I pick epsilon, any epsilon between 0 and r, what I said here is absolutely correct. Okay, that's how small. There is a number r that how small means that epsilon is less than r, bigger than 0. However, r is difficult to compute. We're going to see in a few minutes that r is the smallest positive root of all these polynomials. So that's computationally, that's going to be hard to do. But theoretically, we could overcome not knowing r, because I'll try epsilon. If this doesn't work, we'll try epsilon over 2. If it doesn't work, we'll try epsilon over 4, etc. At some point, I'm going to be less than r and my method works. So theoretically, we could overcome the fact that we don't know r. But the second issue is really the one that we cannot overcome, is that on a computer, x plus epsilon is equal to x. If epsilon is much smaller than x, and on the computer only carries a finite number of significant digits. So therefore, if epsilon is not in those significant digits, then the computer will ignore that epsilon. It will just give you epsilon. So this, on the computer, the computer is not going to do this operation. It's just going to ignore epsilon if epsilon is very small. So now the next question is, why give epsilon a value? All we need to make sure of is that the right-hand side we need to make sure that the right-hand side is greater than 0 for epsilon near 0. If we can ensure that these terms are positive near epsilon equal to 0, then we could go to the limit and make epsilon equal to 0. So that's, and when we pivot, remember, this is a polynomial in epsilon. So when we pivot, we're just creating more polynomials. So we need to have polynomials being positive in the neighborhood of 0. And that's what we're going to discuss next. So let's do a definition. So I have a vector a0, a1, etc., am, and I'm going to introduce a new term, which is, I'm going to say that this is lexicographically greater than 0 this vector is lexicographically greater than 0 if, and only if, the first non-zero entry is positive. So that's what the definition for lexicographical. In other words, this vector, I look to the first non-zero entry. So if this is 0, I go to the next one. If this is 0, I go to the next one, till I find a non-zero entry. If that entry is positive, then I say that this vector is lexicographically positive. Example. I could take 0, 0, 10, minus 100, minus 1,000. Okay? So this is 0, so I move to the next one. This is 0, I move to the next one. 10 is positive, then this is lexicographically positive. And the other definition is A0, A1, etc., AM is lexicographically bigger than another vector, B0, B1, BM, if and only if, this is the definition, A0 minus B0, A1 minus B1, etc., to the last one, AM minus BM is lexicographically bigger than 0. Okay, so this vector is lexicographically bigger than this vector. We start comparing, we compare the first component. If they are equal, we move to the next component, till I found an index for which they are different. And if that entry is bigger than this entry, then we say that this vector is lexicographically bigger than that vector. So if I do, let's say, 10, 3, 2, minus 1, this is lexicographically bigger than 10, 3, 1, and 5. Okay, so the first two, 10 and 10, are equal, 3 and 3 are equal, and then 2 is bigger than 1. Therefore, this vector is lexicographically bigger than this vector, even though minus 1 is less than 5. We don't care about that. Once we found where they are different, that's determine which way this inequality goes. Now, so a fact if we have a lexicographically bigger than 0, if we have a vector that's lexicographically bigger than, then actually it's equivalent to P of epsilon equal to A0 plus A1 epsilon plus etc. AM epsilon to the power m. This expression here, it's a polynomial in epsilon. This polynomial epsilon is greater than 0 for epsilon less than r greater than 0 for some r. In other words, if this is lexicographically positive, there is a number r such that this expression is bigger than 0 for all epsilon between 0 and r, so in the neighborhood of 0. And therefore, here, if that's the case, then P of 0 is greater or equal to 0, right? And that's what we want. So this fact is very easily proven. So I'm just going to do an example. It's a trivial fact to prove. Let me take a 0, 0, 0, and let's say here I take 12 minus 7 and 1. Okay? This vector here. This vector here is lexicographically greater than 0, right? I have 0, 0, 0, 12. 12 is positive, therefore this vector is lexicographically positive. Now, what is P of epsilon? Well, that's 0. 0 plus 0 times epsilon plus 0 times epsilon squared plus 12 epsilon cubed minus 7 epsilon to the power 4 plus epsilon to the power 5. So this is equal to, so this is 0. I'm going to factor epsilon to the power 3. So here is 12 minus 7 epsilon plus epsilon squared. Okay. So now clearly this polynomial is positive near 0, because this is positive and then this is small, so this will be near 12. So this first statement is obvious just by looking at this expression. But here I'm going to do more than this here, epsilon 3, and this is equal to epsilon minus 4 times epsilon minus 3. Okay, so if I draw the line, that's 0, this is plus infinity, then here I have 3, and here I have 4. So the roots of the polynomials are over here. Okay, so this polynomial has root at 0, at 4, and 3. Now, my polynomial of epsilon is bigger than 0 for epsilon less than 3 and bigger than 0. It's obvious. If epsilon is less than 3, this is negative, so this positive and positive. So my polynomial is positive for epsilon less than 3. So my R is 3. Or is the smallest positive root. Okay? So in this theorem, R is just the smallest positive root. Okay? So this fact is very easily proven. So let's assume that we have a linear program over here in a simplex format. And then what we're going to do is, and we want to throw a right-hand side perturbation. In other words, I'm going to change this right-hand side. I'm going to choose this way of changing it. So I'm going to replace the first element, b1, by a polynomial in epsilon, which is b1 plus epsilon. Second row is b2 plus epsilon squared, and so on. So I made a slight perturbation to the right-hand side. First, so my right-hand side is polynomial of epsilon. So I have m of these polynomials. Right. And if you look to the roots of every one polynomial, they only have a root, they don't have positive roots. So this polynomial, all of them are positive for epsilon bigger than 0 and less than plus infinity. All right? For any epsilon, each right-hand side is strictly positive. All right? So that's good. So this is a valid simplex tableau. And so let's do some pivots, simplex pivot, and let's say we arrived at a simplex tableau, a bar, 0, etc., 0. The right-hand side, b bar, and of course here goes b inverse, right? The basis matrix, and this is c bar transpose. This is -1. This is minus theta 0, etc., minus theta m. Okay, so I arrived at this simplex tableau. And let's assume that from here to here, my rows were always lexicographically greater or equal to 0. How can we ensure that after I do the next pivot, that stays that way? What do we have to do? So let's choose, let's say we want to pivot here, column R, and then pivot row, P. Okay, so we're going to pivot on this element right here. So what happens? What kind of operation do we do? So the pivot row, we have to divide, we have to take this row here and divide it by this element. So the new right-hand side of P, the pivot row, it's just the old right-hand side of P and divided by A bar of PR. Okay, we just have to divide by this element. We want to put a 1 here. Okay, so if this is, so this is lexicographically greater or equal to 0. And I'm dividing it by positive element. We only pivot on positive element. So this new right-hand side of P is lexicographically greater or equal to 0. No problem for the pivot row. How about the other rows? So the other rows, let's say row I, what happened to the row I? I have to put a 0 in this element. So we have to take this row minus a multiple of this row to make this 0. So the new right-hand side of I is equal to the old right-hand side of I minus A bar of IR, right-hand side, and then the pivot row here, divided by A bar of PR. All right? This is the classical pivot operation that we have to do. So how can we guarantee that this is lexicographically non-negative, given that this is lexically non-negative and this is lexicographically non-negative? Well, there are two cases, right? One, if A bar of IR is negative, if this element is negative, then it's obvious that the new right-hand side of I is lexicographically greater or equal to 0. Because this is lexicographically positive, this is lexicographically positive, and then this is negative, negative, that's plus. So there's no problem with that. But if A bar of R is positive, all right, then I'm going to rearrange this and I'm going to write it a different way. I'm going to write it right-hand side of I divided by A bar of IR is lexicographically greater or equal to the right-hand side of P divide that by A bar of PR. So if I have this statement here, this will imply that the right-hand side of I, the new right-hand side of I, is lexicographically greater or equal to 0. It's obvious. So I need to ensure that for all I of IR positive, I need to have the right-hand side of I divided by A bar of IR greater or equal to the same thing for the pivot row. So therefore, I need to choose the pivot row. The pivot row has to be the argument of the lex min of the right-hand side of I divided by A bar of IR, A bar of IR positive. So I need to choose the pivot row so that it is the lex minimum of this vectors here. If I do that, then the next simplex tableau, I can guarantee you that every row is greater or equal to, lexicographically greater or equal to 0. And this is the same ratio for the simplex, except here we're doing it with vectors. We're doing the lex min rather than just the minimum. Lex min of these vectors. So we have a way of keeping this area here, every row in this area, to be lexicographically greater or equal to 0, and therefore every simplex tableau is a valid simplex tableau, because the right hand side is lexicographically greater or equal for epsilon between some number r and 0. All right? Okay, so now we have a way of doing the simplex pivot and keeping every row lexicographically non-negative. Now I'm going to state a fact now. Let's call this the epsilon LP. Okay. And this is just the LP here. The epsilon LP is non-degenerate. Okay, the proof is quite simple, because what is degeneracy? It's having a 0 on the right hand side. But what is the right hand side after we do mini pivot? Any simplex, it's equal to the B inverse times the original right hand side. Okay, which is equal to B bar B inverse times 1 epsilon to the power n. So every row here, every row in the right hand side is a polynomial of epsilon. How can that polynomial of epsilon be 0? In order for it to be 0 near, here's the plus infinity and 0, right, it has to be 0 in a line segment like this. And the only way for that to happen is if the polynomial, remember, polynomial epsilon equal to 0 for epsilon between r and 0 means that all coefficients are 0. That's very easily proven, this fact. Okay? So in order for a 0 to occur on the right hand side, I need, this matrix has to have a row of zeros. Okay? And if this matrix has a row of 0, then B inverse has a row of zeros. Okay? And that's impossible. Because it's B inverse. A matrix that has a row of 0, its determinant is 0, and therefore this cannot happen in our situation. So therefore our linear program here is non-degenerate. Okay, there will be no way, at no iteration will we have a 0 on the right hand side, and therefore the simplex applied to this will never cycle. It will terminate after a finite number of iterations. Okay, so we have a linear program in Simplex Tableau LP, and then we do some right-hand side perturbation as we did before by introducing this epsilon and this matrix, and which this linear program we called it the epsilon LP, and we just proved that this system is non-degenerate for every epsilon between some number r and 0. So if I pick any epsilon and plug it in here, I'm going to get a linear program that's non-degenerate, which means that the simplex algorithm will terminate in a finite number of steps. And as you notice here, we don't really need to give epsilon a value. We just need to update this side here, which leads to another linear program which I call the Lex LP, which is minimize C transpose big X subject to A dot X equal to BI X lexicographically greater or equal to 0. So this linear program is just this linear program minus this column here. So since the right hand side is a matrix, X is a matrix. So every row represents the coefficient of a polynomial in epsilon. Same thing here. So when we say X lexicographically greater or equal to 0, that means every row is lexicographically greater or equal to 0. That's what this means. And here we're doing, here we're doing the Lex min, because X is a vector. So X is a matrix. So C transpose X is a vector, is a row vector. So we want to find the Lex minimum of those vectors subject to X satisfying this equation. So this is called the Lex LP. And of course we have the epsilon LP, which is this, and we multiply by that vector, 1 epsilon and so forth. And then we have the LP. So we have 3 types of linear programs. And all these can be solved by just solving the Lex LP, where we deal only with the coefficient of the polynomial. And this is, of course, is non-degenerate, and applying the simplex will make it converge in a finite number of iterations. So now, how do we carry these calculations? Let's assume that we are doing the revised simplex for the LP. So in the revised simplex, we are keeping track of B inverse. We're keeping track of the right-hand side B bar. And we're keeping track of the multipliers, alpha transpose. Okay? That's what we have at the beginning of each iterations. So this B inverse will always goes in this area here. So the first step we do is, in the revised simplex, we compute C bar, the objective, what goes in here. Okay, and that is equal to C transpose minus C beta transpose B inverse A. Okay. Yeah, also in the revised simplex, we keep track of the BFI, beta. Okay. In other words, we keep track of the basic variable, the index of the basic variable, and which row they are in. Okay, that's beta. So we update the objective vector, and now we choose pivot column. For C bar of I, negative. So we choose an element that's negative. That determines the pivot column. And now 2, let's call that let's call that R. So that's, and then here we compute A bar dot R. That's the pivot column, which is just B inverse dot A dot R. Okay, so A bar Okay, so we copy that, and now we have third. We do the ratios. So here we do b bar over a bar dot r. Okay, for all the entries that are positive. Okay, so let's say it's over here, and over here. So we calculate those ratios, and then we take the minimum. Okay, regular revised simplex for this. If the minimum is unique, let's say the minimum was here. The minimum is unique. There's no tiebreak. So then we'll just pivot. This will be our pivot column, a pivot row. All right, if the minimum is unique. Okay, and that will be the same calculation for this, for the LP, for the epsilon LP, and also for the Lex LP. It's the same. Okay, there's no extra calculation for the other two. So that's that case. But what if we have, let's say, a three-way tie? I did the minimum, and I found the three-way tie. Then the LP is degenerate, and there is no, and the LP, there is no tiebreaker. You just pick any one of them to be at the pivot row, and that's what leads to cycling, possible cycling. But for the Lex LP and for the epsilon LP, we have to break the tie. Remember, we as before, we're gonna compare rows and choose the Lex min of those rows. So then we go to the second. Here they are tied on the first column. So we go to the second column, and that is what? That's B inverse dot 1, the first column, and we divide by A bar dot R. Okay. So we calculate this, and this. Only these three. And then we take the min here also. And let's say this drops off, and I am left with only 2. Okay? Then I keep going. Then I go to the third column. So I bring in B inverse dot 2 over A bar dot R. So I calculate only these two now. And I take the minimum. Okay, and let's say then now I have only one minimum, and I stop there. This will be my pivot row. Okay, and the tie will be broken because let's assume that I still have 2 here, right? And I keep going till the last one, B inverse dot M over A bar dot R. And here and here, and I still have a tie. Let's assume that. Okay, what does it mean? Look at this B inverse dot 1 from here, this row and this row in B inverse, this row and this row in B inverse are proportional to each other. And that cannot happen because it's B inverse. Any matrix that has 2 rows proportional to each other, its determinant is 0. But here this is B inverse, its determinant is non-zero. So we will never have this situation. And therefore, the tie will be broken. Okay, at some point, the tie will be broken, and we'll have a unique winner here. And that will be your pivot row. And then we pivot on that column, and we get another B inverse, so we update B bar, and so forth. Okay? So the only difference between solving this problem, the LP, and the Lex LP or the epsilon LP is when we encounter degeneracy. And in that case, we have to do extra calculation to break the tie. All right? That's simple.